Okay, YouTube, in this video we're going to continue our exploration of finding real zeros, or at least all zeros for polynomial functions, but we're going to focus on what we refer to as upper and lower bounds, okay, these rules here. So we'll put that to use here when we solve for all the zeros of this polynomial, but essentially I want to read through it before we do so. So it says, let f of x be a polynomial function with real coefficients and a positive leading coefficient. So the only stipulation here is that you have a positive leading coefficient and that all the coefficients are real. It says, suppose f of x is divided by x minus c, this factor right here, using synthetic division. So when we're using synthetic division, basically, I'll go ahead and draw an illustration right here. We have our f of x that spans across this entire thing right here. And what we're doing is we're putting x equals positive c out here. But when we do this, let's say we have a positive leading coefficient, positive, okay? Then these conclusions can be reached. We basically say if c is greater than 0, so we say that this is a positive number out here. Let's actually write this down right here. If we put a positive number out here, and we have a positive leading coefficient like this, positive, then we say, and each number in the last row is either positive or 0, then c is an upper bound for the real zeros of f. So essentially, if I had all these numbers in here, who knows what they are, but I keep getting a positive, positive, maybe a 0, positive, positive, 0, who knows. But basically that none of these numbers are negative, satisfying the fact that this was positive and this started off positive, then we could say that this number right here, this would be an upper bound, an upper bound. And essentially an upper bound means that if this happens, then we would know that on our list of possible things to guess from, no numbers bigger than this c value right here could work. So let's say our list of numbers to guess from are, plus or minus 1, 2, 4, and 8. And we say that, do any of these work? And we check 2. And 2 actually doesn't work, but also it doesn't work and it leaves all positives in this last row. Then I could say we can eliminate 4 and 8 from the possibilities because nothing bigger than 2 could work. So now for this lower bound, let's go ahead and draw a picture for it. This is our picture for lower boundary. We say if c is negative, that is, we're assuming that we're starting with a negative value out here. This would have to be negative. But we still have a positive leading coefficient, so this starts off positive. This basically says if c is negative and the numbers in the last row are alternately positive and negative, 0 entries count as positive or negative, c is a lower bound for the real zeros of f. So in other words, if we were to get a positive here, and then a negative here, and a positive here, and a negative here, and maybe a 0 here, and then a negative here, this would count as a positive in this case. If we see this alternating pattern, then we would say that this is a lower bound. And basically, again, with your list of possible zeros, let's say I have plus or minus 1, 2, 4, and 8, or the possibilities that could possibly work with this function. And I test, say, negative 1. Negative 1 doesn't work. But at the same time, I see this alternating pattern here. Then I'm going to say that negative 2 can't work, negative 4 can't work, negative 8 can't work. As a matter of fact, nothing lower than this value right here could work for us. So what I want to do in this video is put all of our tools to the test now and say find all the real zeros of this function. So the first thing we'll do is set it equal to 0 and try to factor it. As a matter of fact, this does factor, and I would encourage that you go through and factor by grouping, but let's just go ahead and assume that it doesn't factor. So here are some things that we're going to do. We're going to start with this. We say that what are the rational roots that could possibly work for this? And it was the set of numbers of p over q, where p is the set of factors for this constant term. So our constant terms factors are 1 and 2. Those are all the factors of 2. And we say, well, now over the the factors of the leading coefficient. So we say those are 1, 2, 3, and 6. So here's our list of possible things that could work with this. What we're going to do is we're going to clean up this list and write in what we call roster notation. So we have 1 over 1, 1. Let's do 2 over 1, 2. Now let's do 1 over 2, 1/2. We'll do 2 over 2. It's already on the list. Then we'll do 1 over 3. So a third could possibly work here. Or 2 over 3. 2/3 could possibly work here. And then last we have 1 over 6. 1 over 6 could possibly be a 0 of this. And then 2 over 6, which we already see on our list here. So this is the set of all possible rational zeros that could go into this. I would actually test 1 or 2 first, but also what I want to do is I want to check now using Descartes' rule of signs the possible positive roots, how many there could be, or the possible negative roots and how many there could be. So what we'll do is we'll look at the variations in signs of our f of x. So I notice that it goes from being positive to being negative. So that's one variation. So we say one variation there. Negative to positive, that's another variation. And then positive to negative, that's a third variation. So number of possible positive roots on this list that could work, it's either 3 or less than that by integers or integer values of 2, integer differences of 2. So now possible negative, what we're going to do is we're going to go back and we're going to find f of negative x. And f of negative x basically would say that anything with an odd exponent is going to switch its sign. If we plug in a negative x for this x squared, it'll stay the same. And this doesn't even have an x, so it'll stay the same. So I would say that if I were to find f of negative x now, I would say that this 6x to the cubed, or to the third, would switch to being negative. And also this positive 3x to the first, it would switch to being negative. And you'll notice that it goes from negative to negative to negative to negative. So already what I know is on this list up here that none of these could work if they're negative. So look what I did. I modified the list to say, look, no negatives. No negatives can work here. So what I'll do is I'll try any of these zeros that we see here now that we're in a position to test these out. So I would say that let's fill in our synthetic division array. We had a positive 6, negative 4, positive 3, I don't need to write the positive 3, and negative 2. And the very first zero I want to try, just because it's simple to try, is 1. So if I said, will 1 work? So I'll carry down my 6, and I say 1 times 6 is 6, 6 plus a negative 4 is 2, 1 times 2 is 2, 2 plus 3 is 5. I hope you can see it already that this is not going to work here, but I'll finish this out. We say 1 times 5 is 5, and then we get 3 here. So we did get a remainder, and what this means is 1 doesn't work. But not only does 1 not work, what I want everybody else to realize in this video is also this. We plugged in a positive number out here, and this had a positive leading coefficient. Look, it's positive. And look what happened to every single number in this last row. Because they were all positive, they could have been 0 also. What I know is also anything bigger than 1 is not going to work as a 0 here. So now all of a sudden I know that 2 is off my list. So that's how we use upper and lower bounds to our advantage here. So now what I want to do is let's try another possible rational 0 here. Why don't we try a half? So if we try this half, we say half, and I still have 6, negative 4, 3, negative 2. Here we go. We'll carry down our 6. We say half of 6 is 3. 3 plus a negative 4 is negative 1. So I'd say, okay, negative 1 times a half is negative a half. Plus this positive 3 here. This is going to be 3.5 or negative 3, or sorry, it'd be 7 halves. 7 halves here. And then take that times a half, we get 7/4. And I also notice that this doesn't work, 7/4. Now, could I call a half an upper bound? I couldn't actually do that because of this negative that I see right here. So now a half doesn't work. Let's go back and try a third. We got to find one that works. So we say 6, negative 4, 3, negative 2, and we'll try a third. So dropping down to 6, we say what's a third of 6? That'd be 2. That'd be 6/3 is 2. We add these up, we get a negative 2 times this 1/3 here is negative 2/3 plus this 3 here. Let's see, this would be 9/3, take away 2/3 is 7/3. And I see that now this isn't going to work also. So now we can cross a third off our list. Let's keep running with it. We would say 2/3. We'll try 2/3. So 6, negative 4, 3, negative 2. We'll carry down our 6. So 2/3 of 6 is 4. 4 plus a negative 4 is 0. Times this is 0. Times 3, or sorry, added with 3 is 3. And then 2/3 of 3, that's 2. And a positive 2. So now we get 0. So the nice thing about this is don't lose this value. As a matter of fact, we said go find all the zeros. We just found one, 2/3. And what's even better about this is this remaining polynomial expression here, this is going to be 6x squared plus 3. We can now just go set it equal to 0 and solve it. And by solving this, we would say we would subtract 3 to this side. This would produce a new equivalent statement of 6x squared is equal to negative 3. We'll go ahead and divide both sides by 6. It's a positive 6. So we get x squared is equal to negative a half. And so now taking the square root of both sides, we actually get this. We get x is equal to plus or minus the square root of negative 1 over the square root of 2, which comes out to be I plus or minus I over the square root of 2. And by rationalizing this expression, by taking it times the square root of 2 over 2, we get this. We would get the square root of 2 over 2, and we'll throw the I off on the side and we'll say plus or minus. So if we wrote this in standard form, we would say that our other two zeros are 0 plus or minus root 2 over 2i. And we can see how those other two zeros there actually occurred in conjugate pairs. So the last but not least, we say, well, how many total zeros are there? We say there are 3. And so we could write this as the product of 3 linear factors. We weren't asked to do that on this one, but I do want to do this. I'd say the linear factorization theorem guaranteed that because this is third degree, then x minus 2/3 is one of our factors. X minus 0 plus root 2 over 2I is another factor. And another factor is x minus 0 minus root 2 over 2I was the third factor. Cheers.